Last time we set the scene for the Deutsch-Jozsa algorithm, and we defined the precise mathematical problem that this algorithm is intended to solve. Namely, we have a Boolean function from a bit string of arbitrary length n to 0 or 1. And the question we address, the problem we want to solve, is whether or not this function is constant or is balanced, meaning that the two possible values of the function, 0 and 1, occur with equal frequency. So if you wanted to check that classically, then you would have to call the function multiple times until either you find for the first time two different values of the function, and then you can stop, then you know it's balanced. Or if the values of the function keep being the same, then you have to call just one more time than half the possible arguments of the function, and then you can be sure whether it's constant or balanced. So classically, you need up to 2 to the power n half plus 1 function calls, which means the number of calls grows exponentially with the length of the input bit string. And I promised last time that the Deutsch-Jozsa algorithm can answer this question for you with a single call only. Now, like Deutsch's algorithm, the Deutsch-Jozsa algorithm uses an oracle, and it looks precisely like the previous oracle. The only difference being that the upper input is actually a bit string of length n, and this is indicated also by the /n on the wire. So if whenever you see in a circuit, you see this on a wire, you see this slash with a little n, then you know that this wire represents actually n qubits rather than a single qubit. And x is therefore not a single qubit, but it represents n qubits. Now, just as in the case of Deutsch's algorithm and the oracle used there, if the inputs are all in, the input qubits are all in basis states, so x and y are basis states. In the case of x, it's a basis state in the n qubit Hilbert space. Then the x does not change, and only the y, so like a control qubit, and the y, like a target qubit, may change, and you add to y the value of the function evaluated for x. And this is an addition mod 2. The first question we should discuss is whether this oracle is indeed a unitary transformation. So in order to be implementable as a unitary gate, this has to represent a unitary transformation. And there's a very simple way to see that. First of all, this oracle maps basis states to basis states. Now, basis states form an orthonormal basis, so that should preserve orthogonality. The only thing you have to make sure is that this map is 1-to-1, that you don't have two different basis states mapped to the same image, to the same basis state. And the easiest way to see that is if you add a second oracle gate after the first one. So you apply the same transformation once again. Then once again, the x remains unchanged. And for the lower qubit, this target qubit, you add yet another f of x. Yeah, maybe I can just very briefly show you this. You have x and y going into the oracle gate. X is unchanged, and the y is modified. You add the value of the function evaluated for x, mod 2. And then you just send these qubits once again through the oracle. And once again, the x remains unchanged. And below for the target qubit, you have y plus f of x, and then once again plus f of x. Okay? But the sum of 2 bits, mod 2, is always 0. Yeah, if f of x is 0, then of course 0 plus 0 is 0. If f of x is 1, then 1 plus 1 mod 2 is also 0. So below for the target qubit, you have again y. So the two oracle gates in a row map basis states to themselves. So together, this is the identity map. In other words, the oracle is its own inverse, which means in particular that the oracle transformation is invertible, and therefore the map is 1-to-1. So in short, you have the oracle maps basis states to basis states and does so in an invertible fashion 1-to-1, and therefore it must be unitary. Yeah, here I marked once again that in contrast to Deutsch's algorithm and the oracle there, the novelty is that you have now n so-called data qubits. Yeah, you don't talk about control qubits like in the C0 gate, but here you talk about data qubits. Now, the circuit for the Deutsch-Jozsa algorithm proceeds in steps that are completely analogous to the simple Deutsch algorithm. And let's go through this circuit step by step. So, as in Deutsch's algorithm, the data qubits, now there are several of them, are all in this basis state 0, and the target qubit starts out in the basis state 1. So this is psi naught. In a first step, you apply Hadamars to all the qubits. In the case of the data qubits, you see that gate H with a tensor n in the exponent. This just signals that you have n qubits here, and you apply the Hadamard gate to each individual qubit. So in the n qubit Hilbert space, you apply the n-fold tensor product of the Hadamard gate. Now, after this initial Hadamard transformation, we can write the state of these qubits in the following form. Let me do the same here on a sheet of paper. So we have H tensor n, and we also have a Hadamard for the target qubit. And now we wonder about the state of all the qubits after this initial step. Now, this state psi1, where the data qubits they start out in the basis state 0, and they are all transformed to the state plus, which has this form. So all the data qubits are now in this plus state, whereas the target qubit is, which started out in the basis state 1, is in the minus state. There's an alternative way of writing this n-fold tensor product. You can just multiply it out and write it in the form that's 1 over square root of 2 to the power n, or 2 to the power n half. And then we have a sum where x goes, where you sum over all possible bit strings of length n. And then you have the n qubit state x, basis state x for the n qubits, tensor minus. After these initial Hadamard transformations, you call the oracle. We have the oracle, and this transforms the state psi1 to another state psi2. Now recall from the last lecture on Deutsch's algorithm that there we found the eigenstates of the oracle. For Deutsch's algorithm, we found that the unitary transformation associated with the oracle applied to x minus, so you have x and minus going into the oracle. We found that this gives minus 1 to the power f of x times x minus. In other words, the state x minus is an eigenstate of the oracle with eigenvalue plus or minus 1, and specifically it's minus 1 to the power f of x. Yeah? So here going out you have minus 1 to the power f of x times x minus. This result that we found for the oracle in Deutsch's algorithm still holds when you have n data qubits. So in that case, maybe it's better to write that with the tensor product, so x tensor minus, yeah? And x is now an n qubit basis state, and then it is still true that is minus 1 to the power f of x, x tensor minus. Yeah, so this is a result that we found last time when we discussed Deutsch's algorithm, which carries over to the more general case with n data qubits. And we are going to use this result now to calculate the state after the oracle. So using that result, we get psi2. We have here, we've brought psi1 in a form where we have a sum of various terms, and each term is a tensor product x tensor minus. And we learned that x tensor minus is an eigenstate of the oracle. So we can immediately use that result and find psi2 is 1 over 2 to the power n half, sum over all x. And then we have minus 1 to the power f of x, x tensor minus. After the oracle, we apply Hadamard transformations once more, but only to the data qubits. And we obtain a state psi3. Now here I would like to use another result, this time a result about the Hadamard transformation. Hadamard applied to the basis state 0 gives the plus state, which is 1 over square root of 2, 0 plus 1. And the Hadamard transformation applied to the basis state 1 gives the state minus, which is the same, just with a minus sign in between. One way to write this in compact form is to say Hadamard applied to basis state x. So x is 0 or 1. Is 1 over square root of 2, and then the sum over z, where z is also 0 or 1, minus 1 to the power x times z times basis state z. Okay, let's just try it out. For x equal to 0, then we have here, well, then this is always plus 1, yeah, and then we sum over z, 0 and 1. So here the sum is basis state 0 plus basis state 1, and that fits. If instead x is the basis state 1, then we have, when z is 0, then this is still plus 1, so we have basis state 0. And then when z is equal to 1, then we have minus 1 to the power 1, which is minus 1. So we have basis state 0 minus basis state 1, which gives us this result. Okay, so this formula here is a compact way of writing the effect of a Hadamard gate on one of the basis states. Now, if x is a basis state not of a single qubit, but of n qubits, and we apply the Hadamard transformation to each of the n qubits. So we have Hadamard tensor n applied to x, where x is now an n qubit basis state. Then this formula here applies to each individual qubit. And so we can write this as 1 over square root of 2 to the power n, so which is 2 to the power n half. And then we have a sum over z1, z2, and so on until zn. They are all 0 or 1. And then we get a factor minus 1 x1 times z1 minus 1 x2 times z2 and so on. And then the basis state z1, z2 and so on, z3, zn. Okay, where the x1 is the state of the first qubit in x, x2 is the state of the second qubit, and so on. And this expression can be written even more in a more compact fashion. We can say, rather than summing over the individual zi's, we consider an n, a bit string of length n. So z is now a bit string of length n. And then we have at the end the basis state z, and all the factors minus 1, 2, xi, zi. This can be summarized as -1 to the power x dot z, where this is the scalar product of the two bit strings. So we do this bitwise. It's the bitwise scalar product mod 2. And in this fashion, we have a very compact formula for the action of H tensor n on an arbitrary basis state in n-qubit Hilbert space. This is the formula we are going to use next in our circuit. So we have psi3 now, and the Hadamard transformations, they apply to this basis state x of the data qubits. And we just saw the Hadamard transformations, they produce another factor 1/2 to the power n-half. We can combine it with this prefactor. We get 1/2 to the power n. And we have the sum over x. And we get a sum over z. And we have -1 to the power f of x as before. And from the Hadamard transformations, we get an additional factor -1 to the power x dot z, where this is the bitwise scalar product of the bit strings. Yeah, so both x and z are bit strings of length n. And then we get the basis state z tensor minus. So this is the state after the this latest Hadamard transformation. Next in the circuit, we perform a measurement on the data qubits. What do we expect for the outcome of that measurement? Let us look specifically at the probability that this measurement will produce only zeros. Yeah, so this is the psi3 is the final state after our gates. And now we perform a measurement in the standard basis on the data qubits. Now the state of the data qubits, well, that's a superposition. And they're all, it's a superposition of many different basis states in general, yeah, of these basis states Z. If we want to calculate the probability with which we find all zeros in this measurement, we must consider the amplitude associated with the basis state 0, and so for z equal to 0, and take the absolute value of that amplitude squared. So what is the amplitude? It is 1/2 to the power n. And then it's this expression in front of the basis state evaluated for z equal to 0. So we still have the sum over all x, and we have -1 to the power f of x. And then we have -1 to the power x dot 0 scalar product, but we consider z equal to 0. So the bit string z consists of only zeros. So that is it, squared. This is the probability of obtaining, when we perform measurements in the standard basis on all n data qubits, this is the probability of finding them all in the state 0. And now let's calculate this probability for the two cases, for the two possibilities that we have, that either the function is constant or the function is balanced. If the function is constant, then all these terms here in the sum, they all have the same sign. They are all either +1 or they are all -1. And there are 2 to the power n different bit strings of length n. So we have 2 to the power n contributions to the sum, and they all have the same sign. So this is plus or minus 2 to the power n in the case of a constant function. Then divided by 2 to the power n here in the prefactor, this is plus or minus 1, and the absolute value squared of that is 1. So the probability is 1. In other words, if the function is constant, then we can be certain that measurement on the n data qubits will give all zeros. What happens if the function is balanced? Then in this sum, half the contributions will have one sign, so -1 to the power f of x will be, say, +1, and the other half of the arguments will give -1. And when we add them all up, they cancel each other, and this sum will be 0. And therefore the probability will be 0. This means that if the function is balanced, then it is impossible that measurement on the n data qubits gives only zeros. It is certain that at least one of the data qubits, at least one of the measurements on the data qubits will give 1. And this means we have a way of distinguishing constant from balanced functions, because if we see that the measurements yielded all zeros, then we know the function must be constant. And if there is at least one in the measurement results, then we know for sure that the function must be balanced. So indeed, we could decide whether the function is constant or balanced by running this circuit just once, and in particular by calling the oracle, calling the function just one single time, as promised.